Okay, so first, who am I? I was one of the main engineers and designers of RabbitMQ. So if you're currently suffering from RabbitMQ, particularly to do with high availability or clustering or mirrored queues, I apologize, that's probably my fault. But lessons have been learned. So I no longer work on RabbitMQ. So I'm working on a product called GoshawkDB. It's a relatively young database. It's been in development a couple of years. This talk is about how Goshawk compares to some other products on the market, some of the algorithms that Goshawk uses, and how and when you might choose to use Goshawk. The first release of Goshawk 0.1 happened just before Christmas last year. 0.2 was about 4 or 5 months ago, and 0.3 is going to come out in the next couple of weeks. But first, I need some audience participation. So could you raise your hands if someone comes up to you and asks you questions about a particular database, would you be confident in your answers, particularly about the features and semantics? So first of all, MySQL or MariaDB, who's particularly confident about that? Okay, we've got one. What about if it's about the Spider storage engine or Galera clustering? Wow, no one. Okay, PostgreSQL? One. Oh, okay, half a dozen, brilliant. MongoDB? 2, excellent. Cassandra? Couple, okay. You know a lot. Okay, fine. So in this first part of the talk's in 2 parts. The first part of the talk, we're going to be talking about different databases and how you can try and compare them. So I want to put us in the situation that we are starting a new application and we think we're going to need to use a database. So how do we select that database? Well, we might start by coming up with some sort of features, requirements list. So we might decide we want it to be distributed, because everyone wants distributed things these days. But immediately we have a problem. What does this actually mean? Does it mean, okay, we've got a cluster of nodes that make up this database. Can I connect to any of them and submit any query to any database? Or do I only have to connect to a particular primary node? If that primary node fails, how do I discover the new primary node? We probably want it to be fault tolerant so that we can continue working in the face of failures. So that means that data is going to have to be replicated between different nodes. How many nodes? How many replicas do we want? So that's another question to answer. We might want automatic sharding as well. So by this, I mean that sure, data is replicated, but we might not want every single node to know everything. Because if we do, then that might then mean that as the cluster gets bigger and bigger, performance is actually going to drop off because we're going to have to spend more time distributing data about. Do we want it to be transactional? We don't always need it to be transactional, but transactions are a really powerful feature. They compose by nesting. They often make the code that we write on our application a little bit simpler. But as I say, we may not always need them. Most importantly, we want it to be intuitive. We want to have a clear model in our mind as to how this database is going to behave, particularly during failures, because it's when everything's on fire and there are lots of failures going on that we really need to trust the database to do what it claims it's going to be able to do. And obviously, we need it to be fast enough as well. Now, we're just starting out an application. We may not have exact performance requirements, but we should have a few orders of magnitude accuracy. So we should be able to say, are we doing 1,000 operations a second? Are we doing 1,000,000 operations a second? And obviously, that's going to have an impact on our choice of a database. So I'm now going to talk about some of those databases I mentioned earlier. 3 things. I'm not an expert in any of those databases. What I'm presenting here is I spent about half a day reading documentation on each one. So if you're sitting there and you know I'm wrong, please stop me and correct me. I have no intention of spreading misinformation. Number 2, please don't interpret anything that I'm saying here as criticism. All of these databases are really, really popular, and often for really good reasons. They clearly meet the requirements of a lot of people. And finally, I'm going to be introducing a lot of terminology here without explaining it. And that's sort of the point. The point is that in order to understand these databases, we need to understand a lot of terminology. We need to know a lot about how these databases actually work. So first of all, MariaDB, is it distributed? Yes, it does a primary secondaries designed by default. You can use this Galera stuff, which sits on top, and that gets you full multi-master. So that means that you can connect to any node within the cluster and submit any query. Is it fault tolerant? Yes, Galera, for various reasons, has to be a CP system, which comes from CAP theorem. So there is a majority of nodes, and provided you're fully connected with that majority of nodes, you should be able to submit queries and it should continue working. If a node fails and then joins back in, apparently it will automatically resync. The documentation suggests that might be a slightly expensive thing. I don't know, I've not actually tested it. Can it do automatic sharding? Ish. Galera itself can't, but there's this other thing called the Spider storage engine, which apparently can, and you can put that on top of Galera. Is it transactional? Yes, but with Galera you only get weak isolation levels only, so the maximum isolation level you can get is repeatable read. So is it intuitive? It's a bit complicated. Again, please don't take any of this as criticism. There is a lot of documentation about limitations, and that's really, really great. It's really important that this documentation exists, and that is completely illegible. But what I worry about with stuff like this is I would love a tool which can verify when I check in code that my code isn't violating any of these constraints, because I want confidence that my code's going to do the right thing. So it's really important to have tooling around this sort of thing. We can also start to build up a list of extra terminology that we need to understand. So we've got CP, we've got isolation levels, and we've got this thing about how do we actually validate that our code is safe to run in a cluster. Moving on, MongoDB, is it distributed? Yes, it's definitely a primary secondary design. The documentation, I may have misread this, but it sort of suggested to me that you always have to connect to the primary, even if you're just doing reads. I might be wrong on that. Is it fault tolerant? Yes. Again, it's a CP system, so there's this fully connected majority of nodes thing. Does it do automatic sharding? Yes, this is built in. Within Mongo, you can do sharding. It's on the collection level, and there are several different strategies available. Is it transactional? No, absolutely not. Mongo doesn't try to do any transactions. Is it intuitive? Well, as with all of these systems, there's a bunch of terminology you've got to learn. You've got to learn the APIs and stuff. So there's a thing called write concerns and read concerns. So that's when you submit an operation, it's the number of nodes that have to essentially duplicate the operation and agree on the outcome. Again, there is a bunch of documentation, really important this exists, about how to use this stuff safely. It would be great to have some tooling around this. Okay, and then we can add to our list of stuff that we need to figure out. So we've got write concern and read concern. We've got read preference. So that is when you submit a read query. You might want to indicate that you don't worry. You don't have any worries about this query being performed on the primary. You're perfectly happy for it to be performed on a secondary node. Moving on, Cassandra, is it distributed? Yes, completely. You can connect to any node and submit any query to any node. Is it fault tolerant? Yes, completely differently. There's a replication factor, which is the number of copies of each piece of data. There's a thing called hinted handoff, which means that if you have got lots of failures going on so that your replication factor can't be made, but your write concern is lower than your replication factor, you can still make progress because the hinted handoff stores on the local node the handoff. If you've got two clients writing to the same value at the same time, how do you decide which one wins? Well, in Cassandra, it's LWW, which is last write wins. The problem with that, though, is that the last is defined by a timestamp, which I believe actually comes from the client, and the timestamp is just a pure physical clock, so it's your NTP time. So that sort of doesn't work because clocks drift. So it's not last write wins, it's some reasonably recent write wins. Does it do automatic sharding? Yes, Cassandra does it based on consistent hash ring. That sort of has its own problems. You don't actually get uniform distribution with a consistent hash ring. I don't have time to go into that here. Is it transactional? No. It does support something called lightweight transactions, which allows you to do a bunch of operations on the same object and make those things atomic and isolated. There are some question marks about how that's currently implemented. But I have been told that it's currently being re-implemented, so I'm sure it's going to get better in the future. Is it intuitive? It's very flexible. So you can go all the way from an AP system where it doesn't matter how many things are on fire, you should still be able to get it to do some work for you, right up to a system where it will give you lots and lots of guarantees. So again, we can add more stuff to our list of terminology. So we now have CP and AP, so that's the CAP theorem. We have last right wins. We have timestamps and clocks, so we've got physical wall clock time. We might also want to start thinking about hybrid logical clocks and ways of solving problems with clock skew. We have consistent hashing. There are lots of different ways of implementing that. Some ways are better than others. We've got Paxos, which is a consensus algorithm. We might also want to think about other consensus algorithms. There are lots of those. So let's have a quick look at a couple of these. CAP theorem, I'm really not going to talk about at all in this talk. For three reasons. One, I don't have time. Two, I'm certain that there are other people giving talks here who are going to cover that very, very well. And three, I don't actually think it's a particularly great way to compare different databases. I think there are better ways to compare databases. So let's have a quick look at isolation levels instead. So here is a chart of isolation levels. We've got some words and they're in a tree, well, a graph-like structure. So the simplest thing and the most intuitive thing is the thing right at the top, strong serializable. So a database that implements strong serializable has to behave as if it is performing one transaction at a time. It runs the transaction right the way through to completion before starting on the next transaction. Now, if you're implementing that, you obviously don't have to implement it that way. You can apply as many optimizations as you want, but the behavior has to be equivalent to one, which only does one thing at a time. So over here we have serializable, we have repeated read, which is the thing from Galera. We have snapshot isolation, which is the default isolation level of an awful lot of databases. So let's have a quick look at snapshot isolation. Oh, and basically, as you go down this chart, more and more weird stuff happens, and it's inherited. So serializable is a bit weaker than strong serializable, and the weirdness that it introduces, well, snapshot isolation has the same weirdness plus a little bit more. So let's have a look at snapshot isolation. This nice one-sentence definition. It's guaranteed that all the reads made in a transaction will see a consistent snapshot of the database, and the transaction itself will successfully commit only if no updates that it has made conflict with any concurrent updates. So a transaction is going to start, we take a snapshot of the database, all the reads are run against that snapshot, and we keep a record of all the writes that the transaction has made, and then when the transaction commits, we compare those writes to any other writes that are going on at the same time, and we see do these things conflict. If you are unlucky enough to be running Oracle, then you can put Oracle into serializable mode, and you don't get serializable. You get snapshot isolation instead. But in general, just don't use Oracle. Okay, so I mean, this is a great little one-line definition, a specification. You can look at that. You can probably go and implement it. It doesn't tell us anything about what can go wrong. So let's have an example of what can go wrong. So here we are going to have two clients. They're both going to connect to the database at the same time. They are going to submit transactions to the database at the same time, T1 and T2. And this database only contains 2 bits of state, X and Y. So under serializable, the database is going to have to choose to run one transaction and then the other. So we can start with T1. So is X equal to 0? Yes, it is. Okay, so we can do our assignment. T1 can then commit. That's all fine. Then T2 will start. Is Y equal to 0? No, it's not, because we've just modified it. So T2 commits, but it doesn't do any further work. So we're left with X is 0 and Y is 1. And obviously under serializable, these transactions were submitted concurrently, so the database could choose to do them the opposite way around and get the exact opposite result, no problem. Under snapshot isolation, there's a third thing that can happen. So snapshot isolation can do these two things, and most of the time it will. But under extreme load, it'll do a third thing, which is they will happen concurrently. So we follow our rules. The 2 transactions start. We take snapshots of the database. So we can then concurrently test, is X equal to 0? Yes, it is. Is Y equal to 0? Yes, no problem. They can both do their assignments. And then they'll both try and commit. So the rule is we compare the commits, the writes of one transaction with the writes of the other transaction to see whether they conflict. And here they don't, because they're actually writing to different objects. So we get this really weird outcome of X1 and Y1. And so this is an anomaly. As you go down that chart, you get more and more anomalies. This particular anomaly is called write skew. And this is super surprising, right? I mean, how many of us have ever tried to deal with this sort of issue in production? I mean, have we ever written code that tries to detect this and undoes this? This sort of thing is going to happen when half your cluster has failed, you've got more users than you ever estimated, and suddenly you've got weird corruption in your database that you may not even be able to detect. This stuff's really weird. So moving up from snapshot isolation, the one above that was serializable, and the one above that was strong serializable, which is also often called strict serializable. So what's the difference between those two? Well, strong serializable must obey causality, whereas serializable doesn't need to. And this is really surprising. So a simpler example here, we just have one client, which is submitting 2 transactions, one after another, and we have one piece of state. So the client is going to submit T1 and then T2. And most of the time, the server is going to run them T1, T2. But it's actually legal, if certain other conditions are met, for the server to see T2 and to actually go, I'm not going to do that. I'm going to pretend it was done a long time in the past of this database, because there may have actually been a safe point previously in the history of the database where it would have been safe to insert T2. So the causality here is being violated. The client definitely has a causal relationship between T1 and T2. T2 must have happened after T1. The server is actually free to violate that. So the difference between strict serializability and strong serializability is really, really powerful. And as I say, these things are inherited. So if we look at snapshot isolation again, we'll note that there's actually no requirement as to when the snapshot was taken. It doesn't have to be the most recent state of the database. It can be some historical state. Which is what I said there. So then the only thing that I'm going to say about CAP is that we can overlay CAP on top of this. And so we have proofs of this, and so all it's really saying is if you want to achieve any of the isolation levels which are in the top half, you have to be in a CP system. And that's really all I'm going to say there. So finally, we get to GoshawkDB, and obviously it's going to tick all the boxes. So is it distributed? Yes, you can connect to any node and do anything from anywhere. Is it fault tolerant? Yes. In the configuration, you specify a parameter called F, which is your failure parameter. So this is the number of failures you want to be able to withstand. And Goshawk will make sure that there are enough replicas of every piece of data so that you will still be able to make progress so long as there are no more than F failures. Does it do automatic sharding? Yes, completely transparently. As a client, you never need to think about that. Is it transactional? Yes, and it only does strong serializable, and that's kind of rare. But yes, you have no choice at all. That is all you get. So is it intuitive? Hopefully. Strong serializable, I think, is the simplest and easiest isolation level to understand. Goshawk, it's only 2 years old, so it only has currently a fairly small API and hopefully clear documentation. I sort of have a theory that products get popular and they add more features, and then they get more popular, and then they add more features, and they reach a stage where no one understands what they do or how they do it. And some of these other products may be further down that path. Goshawk definitely isn't, and I'm trying to resist adding unnecessary features just yet. So the conclusions of part 1, understanding databases is hard. There is a lot of terminology which makes comparing them very, very difficult. In my experience, it's very common that your requirements will grow over time. So you'll start on an application and you'll think, well, we don't need transactions, we don't need strong isolation levels, let's just use something simple. And that will be true for month 1, month 2, month 3, but 6 months, a year down the line, you'll suddenly be implementing a feature and you'll think, oh, I really, really wish that I had transactions, or I wish that I had, a stronger isolation level or something like that. So I would advise, and again, obviously I'm going to say this, hedge your bets. Go with something that gives you very, very strong guarantees and simple semantics to start with, provided that it's fast enough. Now, obviously, the more work and the more guarantees that a database offers you, the more work it has to do per transaction. So it is going to be slower. Now, you can optimize and do a good job at implementation, but ultimately, something that offers you very, very strong guarantees is not going to be suitable if you're doing some, really high volume clickstream type stuff. So, horses for courses. And then, as we've heard earlier, actually, with the cockroach talk, at scale, problems stop being rare. So we've learned this from Google and Netflix and Facebook and Amazon. you're writing some code and there's a feeling in the back of your head and you dig into it and you discover, actually, yeah, there is a race condition between these two different things, but I reckon I'm going to be able to get away with it. This sort of events, these aren't going to occur in practice, in production. Well, actually, they will. Stuff will be on fire. You'll have more users than you expect. And these sorts of things will occur. These race conditions will occur. And actually detecting that these race conditions occur and you've now got corruption in your database can be an absolute nightmare. OK, so part 2, APIs. Most databases have some sort of query language. And obviously, SQL is the standard query language. It's been around for a long time. And for a lot of use cases, it is absolutely the right choice. But it's not always the right choice. Over the last 10 years, we've seen a move away from SQL and towards no SQL, but really that's just replacing the S. There is often still a query language of sorts. Goshawk is about as far away from a query language as possible. So Goshawk doesn't have tables or rows. It stores objects. So what does the API look like? Well, when a client connects to Goshawk, it gets told about a root object. And so from there, it can inspect the root object, and it can see whether it's got pointers to other objects. And as it discovers more pointers and more objects, it can navigate over the object graph. And you can have an object graph of any shape. So we've got some aliasing here. We've got 2 objects pointing at the same object. You can have cycles. You can have bigger cycles. There is absolutely no restriction here. So why have I chosen to do this? Well, in our programming languages, we're really good at dealing with objects. This is how we model the world. So why not just make some of those objects persistent? Why go through this whole rigmarole of translating our objects and all of our state over into tables and rows and stuff, when a lot of the time we don't need that? Now, sometimes we do need that, but not always. And another way to think about it is, imagine a perfect world where our computers have infinite RAM, we've got more than enough CPU, and our hardware never fails, and our applications never have bugs in them. How would we actually write programs and manage data? Would we use a database at all? And I think for a lot of cases, we wouldn't, because we have all the necessary data structures to manage large collections. Dealing with a collection of 1 million objects in a hash map is straightforward if everything's in RAM. So I think a lot of the time, in this scenario, we wouldn't use a database. So it then raises the question, well, what are we actually using databases for? So we use them for persistence. We use them to share data between different clients. Maybe we've got lots of copies of the same client for performance. Maybe we've got different clients doing different jobs. But basically, we're using the database to regulate access to shared state. So if that's all we need it for, then again, do we actually need tables and rows and columns and something like SQL? Or is it much more intuitive to have just persistent objects and an object graph? But it depends on what you're using it for. Okay, and if we're doing that, that means we can get rid of object relational mappings, which I've never liked. So they do weird things. They tend to do 1 table per class or per type, which introduces unnecessary contention. You have objects which have nothing in common apart from they're the same type, and yet they're shoved in the same table. And so if the table's got a primary key, then on inserts, you then have contention for that. It introduces attention as to who actually writes the SQL, because the tools sometimes produce inefficient SQL because they're trying to work with lots and lots of different databases. They sometimes do strange things to your schema. But generally, it's another thing to go wrong. It's another layer of complexity, more things to debug, more things to understand. If we don't need it, let's not use it. OK, so I'm now going to briefly talk about some of the algorithms that Goshawk uses. Distributed databases, especially ones that offer strong guarantees, the most complicated thing that they have to do is for every pair of transactions, any nodes that are involved in any pair of transactions have to agree on the order of those transactions, and that's the most important thing. That is the subject of a completely different talk, and I can talk for hours about that sort of stuff because it's very, very complicated. So I'm not going to talk about that in this talk. I'm going to talk about some of the other algorithms that we use. Goshawk uses MVCC, which just stands for multi-version concurrency control. Lots and lots of databases do this. It's really just a way of versioning your objects. It's no more complicated than that. So here we have our object graph. Every object has a unique identifier. So this is exactly the same as in memory. You can't have 2 objects at the same address. So it's completely analogous there. So we start by giving everything a unique ID, and then objects also have a version number. And so we might be able to compare 2 different versions of the same object. Now, in Goshawk, the only comparison that we can make is one of equality or inequality. We can't order things based on their version number, because as I say, ordering is a very complicated thing, and that's handled separately. But what we can say is that objects which share the same version number must have been written by the same transaction. So in the middle here we have F, G, and I, all of which are at version 5. That means there was a transaction 5 which wrote to F, G, and I. So we can also look at this from a timeline point of view. So this is from the server's perspective. We've got 5 objects here, A through E. They all start at version 0. So the server is going to receive a question from the client. And so the client says, OK, I've just run transaction 3. Transaction 3 read A at version 0, it read B at version 0, and it wants to write to C. And the client is saying, is this OK? Is this still consistent with the state of the database? Well, is it? Yeah, I mean, A is at 0, B is at 0, so that's fine. So this can commit. And so what happens is a read doesn't modify the state of anything, so A and B stay at version 0. C, however, moves to version 3, and so the version number that it takes is simply the ID of the transaction. And so that's one of the reasons why we can't actually order things by version numbers. And then another transaction arrives, transaction 2. This reads B at version 0 and reads C at version 3. So this is very interesting. We immediately have a dependency here. 2 must have come after 3 because 2 reads something that 3 writes. So can this commit? Yes, absolutely no problem. And again, the objects that were written, D and E, they change their version number to take the ID of the transaction that wrote to them. Now we receive a problematic transaction. So this is transaction 7. It reads B at 0 and it reads D at 0. So we can try and draw this in like this. This crossing line, this immediately is a signal that something's wrong. Now we might actually have some other information. We might have some causal information. We might know that 7 is definitely happening concurrently with 2 and 3. So we might attempt to reorder it. But actually in this case, even if we try and move all of this stuff back in front of 3, that would actually violate some of the dependencies of 3. So we have no choice. We have to reject this transaction. And what will actually happen is the server will say to the client, no, this can't commit. The reason why it can't commit is because you've tried to read D at 0, but D has changed to version 2. So here is the new value of D at version 2. Go away, rerun the transaction, and come back to me. And then finally, we receive transaction 4, which reads C at 3 and writes to B, C, and D. And so this is just showing that you can have a transaction that both reads and writes to the same object. OK, so the question that is being asked here of the server by the client is quite different to how a lot of traditional databases communicate from client to server. So if you look at the life cycle of a transaction on a traditional database, it would look something like this. The transaction will start, the client will ask a question, try and fetch some data from the server, it'll get a response, it'll request more data, it might make some sort of modification. Finally, the transaction will end, we'll try and commit, and hopefully get some acknowledgement. Now, we've got a lot of round trips to the server here, so this can hurt performance. And so one of the ways that, for example, SQL has tried to deal with this over the years is it's implemented more and more commands. So if you think about something like upsert, which is now reasonably widely supported, it's a combination of a select followed by a conditional insert. And yes, it means that we write slightly less code on the client, but we have to learn more stuff. But it importantly reduces the number of round trips to the server, so it will go a little bit faster. And in the same breath, we can also talk about stored procedures, which is, again, trying to reduce the number of round trips, make stuff go faster, get the code into the database itself. Goshawk's design is very, very different. So in Goshawk, we assume that the client contains all the data that you need for the transaction. We just assume that. So the transaction runs to completion on the client only, no communication at all with the server, assuming that the cache does contain everything. And then right at the end, we just need a single round trip to the server saying, this is what happened, is this OK? And obviously, the server can turn around and say, no, it's not OK because your cache is out of date. Here are some updates. Go away and run the transaction again. So this changes the question that the client is asking of the server from something like, what is the value of X, into are these reads and writes and actually creates as well? Are they consistent with the current state of the database? Is it safe to apply this? And so if we go back to this diagram, well, this explains the nature of these questions that are being asked here. This is the final commit. It's a record of what happened in the transaction. Can this be safely committed? But I'm sure a lot of alarm bells are going off in your heads because obviously it's clearly insane to ship all the objects from the server down to the client because there are going to be millions of them. So in Goshawk, objects are loaded on demand, transparently, behind the scenes, as you navigate that object graph. So you only bring down what you actually need. And we have, in our programming languages, data structures which are really good at dealing with big, large numbers of data. We have hash maps and stuff. Like with a hash map, you have a million objects in it. If you want to do a lookup in it, you only need to access about 10 of them. And we have exactly the same data structures in Goshawk, so you don't need to bring down everything. So you know there is no problem here. And if we think about it in a normal database-y way, it's exactly the same as just adding an index, because we all know that a linear scan over a huge table is going to be very expensive. So we reduce the number of objects that we need to access, and so we have exactly the same thing here. Okay, so I'm now, just to finish with, I'm just going to give a quick example of how we might design something to work with Goshawk. And really all I'm going to be demonstrating is there are a lot of object-oriented design lectures that I skipped at university. So we can have a customer record, and that will contain a name and some email details, and it will contain its own little collection of orders. And this is exactly how we'd model it in Java or any other language. We wouldn't shove all of the orders together from every cluster, every customer, in one giant great table. So we have our orders, and they have items in them, and again, it will just have a little collection. And so we get the encapsulation that we're always used to. And finally, yes, we might want to track the state of orders, so we might want to have a collection of incomplete orders, so that we can keep handle on that. And we get pointer sharing. So if two orders order the same item, well, we don't have a copy of the item. We just get pointer sharing, which, yes, you can do in SQL and do joins and stuff like that. But yeah, you end up with something where your data in your database actually properly reflects the state of your objects, the state of your objects in your programming language. So the actual API for accessing an object within a transaction, once you fetch an object, it is just kind of get the bytes array out of it or write the bytes array into it. And that is really it. So you're free to choose any serialization format you want. The object is completely opaque to Goshawk. It really doesn't care. But Goshawk allows you to wrap all of these operations up into transactions. Transactions can be nested. So that means you can write nice composable APIs. We've got libraries which can be easily reused. And it's really quite a natural way to work. And in many ways, if any of you are familiar with software transactional memory, it's a lot of the same ideas from that as well. Okay. In conclusion, databases have a habit of going wrong once everything else is on fire. And it's not really going wrong. It's just most of the time they behave in a way that we think is intuitive. And only when they're under a lot of pressure. So, for example, you can write soak tests. You can write benchmarks and things like that, which will demonstrate what actually happens under snapshot isolation. And it's only under those stressful conditions that they will actually demonstrate their real behavior. And it's documented, but you have to learn a lot in order to understand what those terms actually mean. The easier it is to understand the semantics of the database, the less you'll be surprised by it. So that is why I picked strong serializability. It is the simplest thing to understand. In my opinion, we don't always need tables or query languages. Yes, there are lots of use cases where you do, but we don't always need it. And a lot of us, I don't think, are dealing with millions and millions of events per second. And I think there's a slight skewing from the industry when big companies produce very, very impressive results, don't get me wrong. But are those solutions really applicable for all of us? And so, yeah, we can get away with something that hopefully is a little bit more intuitive. Thank you very much. I seem to have lost Chris, but yes, questions, Martin.
If I want to look up something by a string, say like a user by their email address or by their username, how would you model that in terms of this object model? And can you do things like ensuring uniqueness so that
Yep. In Goshawk there is a collections library, which is just something, a bunch of code that is written on top of the standard clients. So there's a client in Java and a client in Go. And one of the collections that I've implemented is a linear hash map. So you would just use that, and so your keys, the API expects it to be a byte array, and the values are just a pointer to an object. So you would just use your string and just get the bytes of that, and that would be your key in your collection. So it's not that the database doesn't present itself as a key value store. It's that you are essentially choosing to use it in that way. Does that
mean the entire hash map is one single object in Goshawk, or does it split across many?
The implementation, so every bucket will be an object, and then essentially the key value pairs within each bucket are pointers. I've implemented so for example, I implemented a skip list where every single key value pair was a number of objects, and there are performance issues there. So if you end up with transactions of thousands of objects, you are actually paying CPU cost for every single object within a transaction. So I've deliberately tried to select data structures which are a little bit more efficient than that, but equally you want to avoid essentially a single point of contention. So there is a balancing act to be done there. Yeah. Anyone else? Yes?
You talked about updates, and that kind of makes sense. If you just were reading data, do you have any control over kind of like, I'm happy to use a stable copy, or actually I really want to make sure this is the latest version, I'm happy to make that trade?
Yeah.
Or is that all just implicit behind the scenes, and you may or may not get the latest version?
You will always get the latest version of some definition of latest. Ultimately, we are dealing with relativity here. Computers go at different speed and all the rest of it. If your transaction runs to completion and your cache is hot, you can get right to the end of the transaction and you can say abort. And so within that transaction, you have read values, you've read what's cached. You're choosing not to commit it. So you're choosing, if it's a read-only transaction, this is safe. You're choosing to say, I don't actually mind if my cache is out of date. So you can control that. You're essentially skipping the validation right at the end of the transaction.
Okay, I'm completely lost here now. So if I was just had a read-only transaction, I was writing data out somewhere else, and I wanted to make sure I had the latest copy of the data,
Yep.
but I'd already got a copy that was fairly recent.
Yep.
And would I commit that transaction, and then I can guarantee that I would have had the latest versions?
So in any system which is strongly serializable, you can't do any side effects within a transaction. Or you shouldn't, right? So it's only when the transaction has finished, because the transaction might have to restart several times.
So you're talking side effects on the client side?
Yes. Yeah. So
Right, okay. That
if
makes sense now. I see.
okay, brilliant. Anyone else? No? Okay. Thank you very much.